100 years ago, two of the greatest minds in science, Albert Einstein and Niels Bohr, stood on opposite sides of a profound debate. At the heart of it, a single question: is the world truly as strange as quantum mechanics suggests? Now, in a lab at MIT, scientists have carried out an extraordinary experiment, one that finally brings one of Einstein's most famous thought experiments to life. And the results? They echo Bohr's side of the debate, but not in the way you might expect. Back in 1927, at the legendary Solvay conference, Einstein challenged Bohr's interpretation of quantum mechanics using a clever thought experiment. Einstein believed that particles like photons have definite properties, even when they are not being observed. Bohr disagreed. He argued that quantum objects don't have definite properties until we try to measure them. This disagreement, though technical, touches on one of the deepest mysteries of reality. To make his point, Einstein reimagined the famous double-slit experiment, where light passes through two narrow slits and creates an interference pattern, proof that light behaves like a wave. But Einstein added a twist. What if we attach the slits to tiny springs? As photons pass through, they would nudge the slits ever so slightly. If we could detect that recoil, we would know which slit the photon passed through, revealing its particle nature. At the same time, the interference pattern would still appear on the screen, showing wave behavior, both particle and wave in a single experiment. Bohr immediately saw the problem. To measure the recoil, you'd need to know the momentum of the slits very precisely. But according to Heisenberg's uncertainty principle, the more precisely you know momentum, the less precisely you can know position. And if the slits' positions become uncertain, the interference pattern, the wave behavior, vanishes. So trying to see the particle nature erases the wave nature. In Bohr's view, you can never observe both at once. Nature simply doesn't allow it. At the time, Einstein's idea was brilliant but impossible to test. The momentum transferred by a single photon is so tiny, no technology in 1927 could measure it. But today, in the 21st century, we can. At MIT, physicists replaced the slits with ultra-cold atoms, chilled to temperatures just above absolute zero. These atoms were suspended in space, barely moving. Light passed through them and formed an interference pattern, just like in Young's classic experiment. Then, the researchers gently warmed the atoms, allowing them to jiggle slightly. Now, photons scattering off them transferred detectable momentum, just like Einstein's spring-mounted slits. What they found was stunning. The more clearly the atoms revealed the photon's path, particle behavior, the more the interference pattern faded, wave behavior. Exactly what Bohr had predicted. This isn't just a win for Bohr, it's a triumph for scientific imagination. Bohr's interpretation of quantum mechanics, once only a philosophical position, has now been physically demonstrated. But it's not a loss for Einstein either. His relentless questions pushed the field forward, challenging physicists to refine and test the foundations of quantum theory. Einstein's critiques made quantum mechanics stronger, not weaker. What makes this discovery especially poetic is its timing. 100 years after the birth of quantum theory, and nearly a century since Bohr and Einstein's legendary debate, we're still exploring the same questions, still pushing the boundaries of what we know. Even now, quantum mechanics works beautifully, but its philosophical puzzles remain. Was Einstein right to dream of a deeper, more complete theory? Maybe, maybe not. But thanks to both Einstein's challenges and Bohr's insights, we are one step closer to understanding the strange, wonderful fabric of reality. Thanks for watching. If you enjoyed this journey into the quantum world, don't forget to like, share, and subscribe.